Welcome, everyone, to this special meeting and who didn't get the opportunity to give their talks at the ENC meeting. So with that short announcement, let me turn things over to John.
Thank you, Dave, and good morning, everyone. Good afternoon, good evening, wherever you may be. Very hot August afternoon here in Massachusetts. Glad everyone could join us. A little light on the attendance today. Looks like 54 or so, but well, not surprising. I guess it's vacation time for many in midsummer, as always. Anyways, Ivan meeting number 39. If you guys can believe that, well, our little experiment is continuing to be quite a success, I guess. And of course, MR Resources and Q1 Instruments, always happy to bring the Ivan meetings to you, as we have from the very beginning. MR Resources, of course, been around since 1985, and sort of everything NMR, as it were. NMR spectrometers, magnets, consoles, service contracts, quench magnet recovery, moving and relocation, and so forth. And not to mention, of course, always a very broad line of reconditioned NMR spectrometers available. In fact, three pretty special machines on hand as we speak, all Brooker Avance 3 instruments, 600, 700, and even a 950. So please do get in touch with them, and they'd be very glad to help you out. That said, Krish, over to you if you've got a few words on upcoming meetings for us, please.
Thank you, John. Welcome, everyone. We have an interesting set of topics coming down the pike. We have next topic is industrial application of benchtop NMR. The topic was so popular, there is a lot of interest in participation. So we actually made that into a two-part series. The first part will be on September 15th. It will be led by Travis Gregor from 3M. He'll be joined by three panelists, and then that will be followed as a part two. That will be in November. Again, will be led by Travis from 3M, and three other panelists will be joining him. Look forward to the announcement soon in your email. In between September and November, in October, we are going to have Tim Claridge from Oxford talking about NOVA sequences. That's tentatively scheduled in October, on the 27th of October. And then in December, this will be the last one of the year, will be Murali Nagarajan from Rutgers. He will do an introductory bio-NMR on December 1st. So the details will be posted soon. Some of them are already in our website, and you will see the emails coming down the pike. And John, that's all the announcement that I have. Thank you.
Thank you, Krish, and a very good lineup. Clearly, we are continuing with our Ivan users group well out into the future. That said, Don Bouchard, over to you for a moment or two. If you could give us a few words on Q1 Instruments, please.
Okay, thank you very much, John. Good morning, everyone. Q1 is dedicated to developing new NMR hardware and software to make routine NMR more accessible. Our products include complete systems at 400 megahertz, complete systems up to 600 megahertz with refurbished magnets from MR Resources for a price that will surprise you. We also offer console upgrades up to 600 megahertz in both an economy and a full upgrade, including full automation with our STM probe. We also offer smart tune and match probes for older Brooker and variant systems for improving reliability. Everyone knows that the probe is the key to performance, and our STM probes have a robust hybrid tuning mechanism with faster tuning, unmatched reliability, and improved throughput. Our STM probes have a patented design with tuning that is free from drift and hysteresis, offers excellent signal and noise, and superior solvent suppression, and is engineered by the renowned Q1 team in Zurich, Switzerland. The probe configurations include a variety of both broadband observe, as well as indirect detection, as well as a dual fluorine detection on both channels. Want to know more about Q1? Inquire at q1instruments.com for more information. Thank you.
Thank you, Don, and very capable lineup of machines. Please do get in touch. And as Don mentioned, I think you'll be quite surprised with the prices. Anyways, Dave, over to you once again. And if you would like to kick things into high gear for us, please.
Okay, let's get started. So we will have, as I mentioned, we'll have 2 talks today, each about an hour. And I'll let the speakers control questions. I think some of them may encourage questions during their talks or not. Certainly, if you have questions, leave them in the chat, and both Krish and I will be monitoring the chat. So without further ado, our first speaker is Yue Wu from the University of Georgia, and he'll present a talk entitled Automatic NMR Spectral Decomposition through Computational Fitting of Time Domain Signals. So take it away.
Thank you so much for the kind introduction, David, and thank you so much for all the panelists to give me this opportunity to give a talk here. You can ask your question at any time you want, and yeah, just let me know when you got a question or any place it's not so clear. So, so this is a work that I have done during my PhD time at UGA. And now I'm a postdoc at Stanford. So this work is a collaboration work with Frank, and he did contribute a lot of technical things here. And we call this method SEND. It's a spectral automatic NMR deconvolution. So we kick from the start. How do we collect or analyze NMR data? When we collect NMR data from the raw data from the machine, what we got is this kind of time domain data. It's basically like a lot of decay sinusoids here and there with different frequency and the rates of decay. So it's kind of hard for a human being to look at this data to see whatever is there. So a few decades ago, what people comes up is they do a Fourier transformation on this data, so that they can see all the different peaks located at different frequencies, and they can distinguish different compounds or different anything. So what I'm showing here is basically a pretty regular metabolomics data set. There are a lot of different compounds have peaks, pretty narrow peaks here and there, small molecules. And of course, it's a good idea to do a Fourier transformation and try to analyze data from there. But that's not generally not so enough, especially for experimental MR kind of data for metabolomics. I mean, particularly untargeted metabolomics data set. So for this talk, I'm kind of focusing on metabolomics, but all these methods I will be mentioning here can be totally expanded to other NMR usage, NMR spectral deconvolution. So what's the problem here? As you can see, there are multiple problems here. These red regions, all these spectra are quite highly overlapped. And there are some broad peaks on the green region, and there are some bumpy baselines here and there, and some peaks are huge, some peaks are small. So and some peaks of course have low signal to noise ratio. So traditional to analyze this kind of data set, what people do is they kind of do a targeted analysis, and it's kind of labor intensive in both identification or annotation and also in quantification. So what's the solution here? We're proposing a solution that kind of in parallel with the conventional quantification pipeline. So start from the beginning when we got different samples, warm sample, urine sample, serum sample, we put that into NMR. We got a FID, a time signal, time domain signal, we process, do whatever we want, like facing some kind of baseline correction and some other process. And then we got like not so bad spectrum data. So in the conventional way, we will do like peak picking or integral for some bins and try to quantify those bins or those peaks, and which will have a lot of like manual process. What SAN will provide, this deconvolution method I'm going to talk about will provide is it will quantify, deconvolute each regions into smaller single Lorentzian peaks, which means deconvolute the time domain into individual decay sinusoids, which will give you like all these 4 peaks overlap here will be like end up to be like 4 individual peaks corresponding to 4 rows in the table. Each peak will of course have 4 parameters: their frequency, their peak-wise, which is lambda here, like decay parameters, and their amplitude and their phase. And as we make this process automatic, we got a huge peak table. This peak table can also be like correlated with each other. Of course, with different samples, then we can see which peak is correlated with which one. Then automation can be, some kind of automation in annotation can be come up with. So before I go into any like technical details, I just want to show some of the results first from this SAN method. So the blue line here is the raw spectrum, the red or orange line is the estimation, the sum of the estimation. So we decompose peaks into individual peaks and sum them together to compare with this blue line. And this is a sample from a methanol extraction extracted P1074 warm sample. So it's like pretty tough sample with a lot of proteins and lipase and also small molecules. And so before I go into any like how this method works, I just want to talk about the background, because there have been like a lot of methods, a lot of trials, hundreds of methods in this field to deal with this problem, spectrum deconvolution or spectrum quantification. Those methods can be like separated or grouped into like 4 different groups. You can definitely do like peak picking, automatic binning, automatic bucketing, which should be the easiest way to do. And of course, which is also affected by overlap in both quantification and annotation. And you can also do like reference library-based fitting, which means you got either spectrum with known compound, either from simulation or from experimental collection. And by using those known compound spectrum as like a reference library, then you can do try to quantify those compounds in the mixture spectrum, in the biological like urine spectrum or like warm spectrum. Method here include like Bellman, Basel, like genomics. Of course, when you choose to do like reference library based fitting, then you like choose also to not only ignore those unknown, majority of unknown in metabolomics, but also those unknown peaks can have effects on quantification what we know. So it's kind of limit yourself to a specific compound that you are targeted. And our method is more kind of similar to this third category, which is spectrum modeling without reference. So those methods will do some kind of fitting for the NMR spectrum mixture and try to come up with peaks and individual peaks, try to deconvolute the overlap regions and see how it works. So one method is Kraft by Krish, and there are also other methods come up years ago by Dennis and Yulian. and also some SVD based method, which is like automatic method. But there's still some kind of problem in using this kind of method in the setting of metabolomics. In the setting of, you got a lot of spectrum and like 300 urine spectrum. You want to analyze all these spectrum together. You want to quantify each one of these 300 spectrum. So to do that, you really need quite a lot of automation and global profiling. You don't want to have any like manual process here and there. So those methods still kind of like this part, and which will be the part that our SAN method will be focusing on, which I will show you later. And the fourth category is just purely spectrum curve fitting. The example is just AMNOVA GSD. And as some of the people here might already know, when you do like just spectrum curve fitting by GSD, you got many of those unreasonable shapes of peaks, like quite a non-Lorentzian and quite unreasonable peak shapes. Yeah, which is kind of a little bit misleading. Kind of in summary, it's not so well suited for automatic and targeted metabolomics, which we will be kind of working on here. So a little bit more details on what's the pattern, what's the kind of scenario of metabolomics and targeted metabolomics type of NMR spectrum. So you can get a lot of different sample types: C. elegans, urines, some kind of fungi, serine, cell culture. So they're all really different. They got different amount of protein. Some of them have protein, some of them have much less protein. You might got lipids here and there. So it's diverse, pretty diverse composition of those samples, which cause diverse patterns and problem in the MR spectrum. And you also have a lot of like different amount of like a large number of samples. So usually we can have like from hundreds to thousands of samples, which can take a lot of time if we do it manually. And of course, it's mostly on target analysis in terms of metabolomics, which means we might be able to annotate like 30 compounds, which correspond to like 90 peaks, but the spectrum might have like 500 peaks. So 80%, at least 80% of those things we observe might not be, we don't yet know whatever it is yet. So considering all these problems, this SAN method will be having those three features that that will be quite useful, quite important for automatic quantification of this metabolomics data set. It needs to be automatic processing and deconvolution. And we are working on and providing a consistent procedure for different organism and metrics. And the estimation peak need to be reliable. So the idea here is really we got a process NMR spectrum, and after the SAN process, then we got like a feature table, which each row has the peak. So let's go a little bit details into the process workflow of SAN. If you pay attention to this figure on the right side, in panel A, we collect spectrum. In panel B, we got like the FID or the time domain data. As you know, like time domain data kind of correspond to the spectrum domain data, like it's equally representation. And after that, we do a subsampling in the frequency domain. So basically, it's like a frequency range automatically. Here, for example, it's like 0.1, like kind of range. And which we also have is corresponding FID data. That corresponding FID data will have much less number of decay sinusoid signal there, so it makes the optimization or deconvolution process much easier. So in the model fitting, we are basically fit as pretty similar to other methods like Krish method, and also some of the methods that I mentioned before. It's fitting of this kind of decay sinusoid signal. After that, we got individual peaks and got a peak table. So the kind of new things we come up with will be kind of majorly focused on the model fitting part, as that's a crucial part to make this process automatically and accessible for different kind of spectrum of samples. First, as it is a time domain fitting. Second, we do a kind of informed initial guesses. So as this is like even though we got like a full peak, this is still like global optimization problem, and we use some informed initial guess to start from a good point, not a random guess. We have a hybrid optimization process with global optimization and local optimization. The global one is Markov Monte Carlo, and the local one is interior point method. So as this is a global optimization problem, combination of the global and local method make it easier for the method to like find out the optimum and convert well into the optimal point. And we also have a way to adaptively choose the number of peaks so that it controls the complexity of the model. Across this region has like 4 peaks. We can use a 1,000 peak to fit this region as well, which will probably works better in terms of objective function. But that's not what we want. We want to control the number of peaks so that it represents both simple and also reasonable fitting. And here is more details into this algorithm. So first, we will generate like a m number of frequency windows by binning. Binning is an automatic process that we done in the program, and also by like selecting for each bin, we want to subsample that signal. We do it by like a method called raise cosine window filter. It's basically keep the signal for the bin and try to soft down the boundary to reduce the artifact. So for each bin, as you can imagine, we can do it in parallel. So for each bin, it's all kind of independent. So it's gonna be a way we can run it in either different machine or different codes or processors. For each bin, what we do is we do a subsampling. We get an initial guess of those parameters like frequency, lambda, amplitude, and phase. We start optimization from there, and then we evaluate the optimization result. So it's like an iterative process. At each iteration, what we do is we try to add another new peak by giving an educated initial guess by a vector multiplication, and from that, with that added new peak. Let's say we got 2 peaks right now, added 1, we got 3. We optimize parameter for all these 3 peaks. So 3 peaks will have 12 parameters, and all the parameters will be optimized according to this objective function, which is basically calculates mean sum square, like kind of distance between the experimental signal and the sum of all the peak signal or all the decay sinusoid signal. And after this optimization converge, we try to check whether we got enough peak, whether adding more peak is beneficial or not. So that will depend on this stop criteria here, and which we'll go to more details in the next slides. But this process is the evaluation process is the goal of it is like to choose a hyperparameter, to choose a number of peak, to make it like with enough complexity but not too much. So the stop criteria, we got like 3 different stop criteria. And you can definitely like, we got parameter for those criteria. You can definitely like refine it a little bit if you think that's reasonable choice. But for the current parameter level, it works fine for multiple different data set, simulated or experimental. So the first criteria is whether we got new enough improvement with adding new signal. The second one is whether we achieve a maximum number of peaks of signals. It's mostly 7 by default for now, which is just because the amount of computation we need for like global optimization with that number of parameters. So 7 would be 28 parameters. So, and the third one will be like the initial gas peak, whether that initial gas peak amplitude is too small. So if it's really small, then it might be relatively close to noise. It's kind of, you can definitely like change this number, increase this number to capture those smaller peaks. And that's basically the technical part. And I will talk a little bit about the evaluation of this method in multiple different ways. We evaluate with some system with known ground truth, which include a simulated mixture with both broad peak and phase distortion, and of course a lot of narrow peaks overlap with each other. And we have another like experimental mixture, which kind of like sent to us. It's a 2 compound mixture in DMSO, and with different concentrations with replicates. And we also have another mixture that are more representative, like of metabolomics type of samples. So which is a urine sample with spec in a compound mixture. So it is both complicated as urine sample and also with some known ground truths as we spec in. And we also tested on different like real biological, real world, really complex samples like worm sample, urine sample, all like hundreds of samples. And also we also like tested on C13 serum experiment. The previous mentioned spectrum all kind of proton experiment, but yeah, it definitely works fine with C13 type of experiment. So before I go into any those examples, I just want to show you one like a diagram, one showcase example for this method. So we got like 2 broad peak here and 1 narrow peak. They are simulated, which we know the ground truth. The blue line is as the estimation sum. The red line is the original spectrum, which of course we add noise here. And if we kind of move this small peak, like it will have different overlap pattern with this broad peak. And sometimes it's kind of hard in those middle part. It's kind of hard to detect that there are really like 2 peaks from a human eyes perspective. So how does this method perform? In all these journeys, that these small peaks, these narrow small peaks moving from the right to left in the chemical shift, we are always capable to distinguish all these 3 peaks, and we can quantify like those 3 peaks. Here I'm showing you the quantification of that small peaks, that small narrow peaks. So the x-axis is the chemical shift, the y-axis is the amplitude, the dotted line is ground truth, and the blue solid line is estimation. So as you can see that, if it's like perfect overlap, then it's going to have some clear affection in the quantification. Although the effects is mostly like 20%, it's relatively small for this kind of extreme cases. And of course, this is kind of a targeted analysis with a specific targeted example case. And this another example is about how it works with a simulated mixture. So in this mixture, we got like 100 peaks, 100 pretty narrow peaks with random concentration in different samples. And then we add some broad peak and some phase distortion. So you can see in the A panel, the A panel is the spectrum, all these different spectrum with different concentration, all these mixtures. You can see it's pretty highly overlapped. It's kind of hard for human eyes even. In the middle and bottom panel, I'm showing you the result of the sand deconvolution. So the black line is a raw spectrum. The right line is the sum of these deconvolution peaks. The green line is the true peaks, the ground truth. Because we do the simulation, we know whatever is there, and we can see whatever it looks like. So and the blue peaks are all those estimated peak from the sand method. As you can see that in most cases it is captured pretty well. Although there are some cases that the number of peaks is detected wrong in some overlap region. When there might be one peak in ground truth is detected to be 2 or vice versa. But as a human eye, you cannot be sure like how many peaks there is in those overlap region as well. So this is kind of a visualization or qualitative kind of evaluation of the result. So how about it quantitatively? So here I'm plotting this scatter plot of 3 different like peak parameters. So including chemical shift of frequency, amplitude, and peak-wise or lambda. Of course, chemical shift is like the really accurate. And the amplitude estimation is with a correlation of 88%. The x-axis, the ground truth, the y-axis is the estimation. Most of the dots kind of densely distributed in the diagonal k=1 line. And some of the dots are kind of away. They might be they are kind little bit bad estimated, and they are mostly those regions that are highly overlapped. And maybe we got the number of peaks wrong. If we got the number of peaks wrong, then the amplitude estimation will be wrong as well. So it's also the lambda, which is peak-wise. But most of the points are really like highly distributed in the middle line. So this is kind of a little bit complicated simulated data set. We also test it on the Krish 2 compound mixture, which is actually slightly a simpler example than this computational simulated one. And the result was also, actually was better than this one. But I'm gonna show you some of the more, like a little bit more interesting data set, more kind of experimental related data set here. So this is, as I mentioned before, this is a urine sample. It's a urine spectrum with like maybe 500 peaks, highly overlapped with a lot of different compounds with both lipids and some amount of proteins. And we spec in a mixture of like those 4 compounds in this urine sample, and with different concentration, see whether we can like deconvolute and estimate those the concentration of all these different compounds. So this both like represent the complexity in real world spectrum and also give us the opportunity to with known ground truths. The way to look at this figure is if you take a look at the bottom line, which is the pure urine, the really gray line is the pure urine, and we add 20 different amount of spec-in mixture into the urine sample and collect the NMR spectrum. With adding like more and more amount of spec-in mixture, some of the peak spec-in peak will be increasing, and unfortunately, it also changes the pH of the urine sample and makes some of the peak like moving in NMR spectrum. As somebody will already know here, pH will shift some of the peak by hydration. By shift the peak in the chemical shift direction. And of course, there are some different overlap pattern with different amount of like new spec-in mixture compounds. So after that, then we try to target some of those regions with those spec-in peaks and also with those like urine peaks to see like how good it works. So what do we expect to see? If we spec in like linearly with the same amount, with each time with 20, the same amount of spec-in mixture, then the peak intensity should change linearly as well, of course, after some volume normalization. So as you can see, the x-axis is the spec-in volume, the y-axis is the peak intensity, no peak, sorry, is the amplitude. All these spec-in peak, which is a solid line here, they all change linearly through spec-in different spec-in volume, and as you can already see there with different slope. Different slope because the peak relative intensity is different in the compound spectrum. Of course, if it's a doublet or other peaks that with the same relative intensity, then that's highly overlap in the linear line, as you can see here. And all these dotted lines, they are the urine peaks that doesn't appear in the spec-in sample. Our expectation should be they keep constant, not change at all, and which is almost the case as we can observe here. Another interesting thing that we can see from this figure is at 4.7 and 5.3 or 5.2, there are like two glucose, actually 4 glucose peak. As you can see, all the peak, it doesn't start with like 0 in its amplitude, which is because in the original urine sample, we do have glucose there, which is reasonable. So that's so I already like talk with you about those samples or spectrum. We know the ground truth and see how it works to compare with the ground truth. And here I'm showing you a little bit preliminary result with some samples that we don't know the ground truth. This is a figure that I showed you in the beginning. It is a P1074 warm sample. It's a pretty complicated NMR spectrum. There are 146 samples, and I think the blue line here on the top panel, this data was collected across by Gonzalo and Amanda. They did a lot of work in like cleaning this data and doing all those sampling. So the blue line is the ground truth. No, sorry, the blue line is, we don't have ground truth. The blue line is the raw spectrum. The red line is the decomposed sum. The sand deconvolution peaks, we sum them up to compare with the blue line. And sand process is automatic pipeline for all these 146 samples. And after we can run them automatically, and and we can produce this red line, and we can also produce the spectrum figure that I show you in the left bottom part of this slides. The black line, the black line is the original spectrum, and then I show the red line, which is the sum of these deconvoluted peak and some of the and all these other individual peaks. In blue is all these individual peaks in the deconvolution. And as you can see, it's pretty tough overlap patterns. So how can we say anything about this kind of spectrum? How can we like say anything about whether the deconvolution is correct or wrong? Whether we can really use this method to like deconvolute or quantify this kind of complicated warm sample? We can try to evaluate the quality of the result by a correlation network. So even though we don't know the ground truth of these samples, those samples will share some similar compounds, and those compounds have different concentration in these different samples, which cause peaks to have different intensity. So those peaks will be highly correlated with each other. And if after deconvolution by SAN, after we do the correlation network and find clusters, those clusters corresponding to some known compound or new compounds in those spectrums, then we can have more confidence in this part. And of course, this kind of spectrum also have pH shift problem. And we are currently working on the correlation network part and try to annotate some of the compound here. Then I'm going to show you another pretty tough spectrum. This is a steering spectrum, which means it has proteins, and it's a natural abundance C13 experiment. It's highly noise. You can see that noise level pretty high, huge baseline problem. It's like a roller coaster. And we only need a little bit like minor parameter tuning to deconvolute this C13 spectrum. And from this blue line raw spectrum to this red line estimation spectrum, SAN estimate spectrum. And you can see that magnitude T can be captured pretty well. And we can always change this noise threshold to kind of filter out those peaks that are kind of relatively noisy and pay attention to different level of noise level of peaks. And across, as I said, this needs a little bit minor parameter tuning. We are still working on, and we'll provide different like template or parameter suggestions for either you're doing proton or C13 data, or maybe other data will need slightly different parameters that we can suggest. So all those parts about like whether we can quantify deconvolute peaks and how good are those deconvolution. Here I'm gonna like cover a little bit more about the like whether we can step a little bit further from the deconvolution, whether we can cover because annotation is always a problem in metabolomics. As I mentioned in the beginning, in NMR metabolomics and targeted type of spectrum, you can not really annotate a lot of compounds. I mean, you can annotate like 20–30% of the peaks. That would be great. Which is basically because the amount of human work and the amount of work we need to do 2D, to do extraction, to manual, and also the chemical expert needed for the annotation. So can we do it automatically? If we do SAN, then there is good reason we can do this automatically. So for each spectrum, we can do send it into a peak table, and we can correlate the same peak with other peak in different spectrums, and try to recover the compound clusters. So what happens here is I got a simulated type of spectrum with a large number of peaks with different concentrations. and I mean, with different compounds, those compounds have peak has different concentrations. And there are like 50 examples here, like 50 spectrums here. So the same compounds will have different concentration in all these 50 samples with different like peak heights. After we do that, we correlate all these features, all these peaks, and then we can find clusters, and we can compare the cluster with the ground truth because we simulated, we know what peak is there. And the right line here is the ground truth cluster peaks or ground truth compounds. The blue peaks, all these blue lines here are the estimated clusters. There are like 15 compounds, but I didn't show all of them, just show a few of them here. As you can see, by this automatic process, many peaks of the compounds can be recovered by those clusters, which is pretty good. We already with this number of peaks, it gave us confidence to see what kind of compound it might be or whatever we want to do in the next step. Of course, in this simulation, we don't have pH problem. We don't have like chemical shift variation of the same peak. So that will be the next step that we are still working on to try to find a method to learn different peak within different between different spectrums, different samples. So as you can imagine, this kind of deconvolution workflow with like 100 samples, it's kind of computational intensive, and we are working with this framework called Network of Advanced NMR, which is supported by NSF, which is a collaboration project with 3 universities, UConn, Georgia, and Wisconsin. And it is basically a big project that we got like a lot of NMR machine in those 3 institutes. People can submit their samples on the web interface, and their sample can be processed, can be like collected in any of those institutes. All these institutes will collect the spectrum for you, and then what you'll have is you'll have your sample, your spectrum on the web interface. And at that step, you can choose to deconvolute your spectrum within this computational framework, because in the UConn, in the NAM process, we got NMR box, which is has a huge number of computer and a virtual machine with a lot of NMR software to make it work for all kinds of different processing. So using that computational process, we can deconvolute the NMR spectrum, and we also connected with NMR PEP, of course, to really do the to make some of the pre-processing part easier. So we can so what's the thing here? We can do virtual NMR collection, and then with all these accessible computational resources, we can do the deconvolution, and we will provide different adaptive process for different kind of data. Either you're doing C13 or you're doing proton data. So this is a work done by mostly like supported. I'm led by Omid and Garad, and yeah, they did a lot of work to make this part work. Yeah. So kind of in summary, what we do here, we got one spectrum, we deconvolute that spectrum. We got another different spectrum, really different. We do the same thing, all in parallel. A lot of spectrum, like say like 100 spectrum here. And for all of these spectrum, we do automatic pre-processing, we do automatic binning, we do automatic deconvolution. And then we got a feature table, a peak table for each of those spectrums. Like for 300 spectrums, we have 300 peak table. Then our analysis can be focused on those peak table only, just like transcriptomics. So we can do feature extraction, we can do quantification, we can do annotation to automatic NMR spectral analysis. And the final goal is really to make this process more automatic and targeted for metabolomics profiling, just like transcriptomics. So in transcriptomics, what do you got? You got like, you not only get a read code, you also get like the quantification of isoform, the quantification of genes. Hopefully, after we improve this method, and after that, we can, in a general way, relative general way, do a thing that we can give you quantification of not only peaks but also compounds, and which will really improve the process, the popularity of and target metabolomics. And of course, will be also useful for other ML spectrum. So in the future, what can be the future direction of this method? One way that it can be connected is directly connected with time series MR spectrum, time series metabolomics. So another part of my work during my PhD is to do this RTA extract, which is a time series MR spectrum quantification method. So originally we got a method called CIVAN by HRMS. We basically measure the in vivo metabolomic dynamics. We got all these spectrum that are changing through time, and this RTA extract use a efficient like ridge extraction method to like extract all these features to quantify this MR spectrum. And of course, the good thing is without alignment. So two examples of what those spectrum looks like. I already kind of annotated all those peaks, like those lactate peaks. They're moving pretty wildly because of pH internal change in the samples, which is the result of like a metabolism of this fungi. So this fungi will produce acid through time when it's eating like glucose or other carbon sources. It's changing the pH, and those peaks are kind of changing its chemical shift. Those kind of things will be super hard for alignment method to work. But I mean, luckily this RTA extract method can extract and quantify all these peaks through time, and even for this glutamate region that are pretty well changing and also overlap here with another yellow peak. One thing that stayed, remain unresolved is overlap here. So those peaks that are overlap, as we are just do ray tracking, the quantification is still affected by overlap. But with the combination of RTA extract and SAM, we can do quantification of all these time series MR spectrum through time, and we can also quantify those peaks with overlap. That's one part I think will be super interesting in the future. Especially those time series spectrum need less of alignment for its processing. They should be easier to do in the future, in the near future. Of course, there are multiple other directions we will go in the future, other directions. One thing is to speed up the optimization and to integrate more with the NAM project and support. We are going to need to add new support with new sample types and power sequence. And as for now, we tried like on 3 or 4 different samples. Not much. The main framework basically doesn't need to be changed. Just a little bit parameter change. It might be needed. Maybe it depends on your the initial number of 0 or other like peak noise level, that kind of thing. So this part is mostly will be done in the future by OMID, and we will also do in the future do some peak-wise alignment after we do SAN. After we do SAN, we'll have a peak table, which might be actually easier to be aligned by the spectrum. Spectrum have like 10,000 points. The peak table will have only like 500 points. And we will expand that to 2D data as well, which is directly expandable because we are using a time domain based fitting. Those 2D data are basically like time domain signals. This method is also can be directly connected with non-uniform sampling data. So for those data, because the optimization can be like you can select a mask region you want to include in the optimization function. It's directly adaptable for those kind of data. So this work is supported by many people, especially Art, Omid, and Frank, and also Krish, and also many other people, and also many other either computational resources, funding resources, and department. And yes, that's my talk. And if you got any question, please ask. And you can also shoot me an email or scan this QR code to my webpage. Thank you.
Well, thank you. It's time for questions now.
I have one. This is Krish. I have one quick question. Hardly NMR spectra are hardly Lorentzian, in the sense, practically speaking, they are never fit a clean Lorentzian. How does SAN deal with that? Is that a best fit approximation or multi-fit approximation? How does it do it?
From our test on the urine or worm samples, most of those narrow peaks. I mean, of course, I do totally agree that if your experimental condition or your shaming or your other things are not perfect, then the peak will be different from Lorentzian. And we are still working on how to solve those part of the problem. Like if there is shaming problem, then what we should do, maybe we can try to find the same part. If it's a shaming problem, then we might be able to find like multiple peaks, the same number of deconvoluted peak for the same peak, for different peak in the spectrum, and that can inform us how to do the quantification, maybe by sum up all these individual peaks. But for many of our collected urine samples, many peaks are actually pretty Lorentzian captured by a single peak. Of course, some of the broad peaks are not at all, which we are less interested yet.
But unfortunately, many of the small molecule, not metabolism spectra, small molecule spectra, are shimmed for the best quote unquote line shape, which actually defined by bits at different positions of the peak. That is invariably in almost all examples I have seen, overdone. In the sense they are narrower than Lorentzian. In frequency domain, that seems to be perfectly fine, but in time domain, the moment you say I'm going to fit to a model, whatever that definition of the model is invariably exponential, and then you get into trouble because they are narrower than Lorentzian. The shimming, all the shimming criteria is based upon not line shape of a Lorentzian, but line width of the peak at different peak height, 50%, 0.55, 0.11. They are measuring line width, not fitting to a line shape, which is a Lorentzian line shape. It's what we are forced to. When I say we, I mean that in time domain, we end up forcing to a specific shape, a specific decay function, which is a Lorentzian decay. Exponential decay. So there is no answer to this at this point. I'm just throwing it out as a potential problem. Fundamentally, we face in time domain fitting.
Yeah, definitely. Let's definitely have more talk later. Yeah, so yeah, we probably need to like write some discussion if needed for this part, as people might, yeah, for those non-location peaks. Yeah, thank you.
Then let's thank Yue and for the very nice talk. Just 1 second, I'll be right back. I always forget.
Ah.
But I have to
Gavel.
conclude our meeting with the nifty Ivan gavel. So I will conclude our meeting.
Thank you, everyone.